Welcome students. So let's continue with our NCERT chapter 9, which is Amines, and today is theory part 7, and today we are going to cover section 9.10. This is disclaimer. So first let us see the objective of today's lecture. So after attending this lecture, you will be able to understand the topics which we are going to cover today. So today we will be covering importance of diazonium salt in the synthesis of series of aromatic compounds including azodies. Now, according to NCERT sections which we are going to cover today is 9.10, importance of diazonium salt in the synthesis of aromatic compounds. Then we will solve an example 9.5. Then we will solve one in-text question which is 9.9. Okay, so let's begin with today's topic, that is importance of diazonium salts. So diazonium salts, they are special compounds that play a big role as intermediates in making other chemicals. So first let's talk about their versatility. So diazonium salts, they are highly useful as synthetic intermediates. This means they act as a stepping stones in chemical reactions, helping us build more complex molecules that might be hard to make directly. So diazonium salts, they allow us to prepare compounds that can't be made by direct substitution. In other words, if a certain group can't be directly attached to a benzene ring, we can use a diazonium salt as an intermediate to get that job done. Now, another key point is that diazonium salts, they can be easily converted into variety of functional groups. So this flexibility makes them extremely valuable in organic synthesis, as we can use them to introduce different atoms or groups into a molecule. For example, we can use diazonium salts to form phenol by introducing OH group. So this is important because direct substitution of an OH group onto a benzene ring is very difficult. But with diazonium salts, it is much easier. Similarly, diazonium salts, they can help us prepare benzonitrile by adding a CN group. So this is another transformation that's hard to achieve directly, but it becomes simple using diazonium salts. Next, diazonium salts, they can be used to make nitro compounds and azodies. So if we talk about azodies, so they are especially important in the textile industry for coloring fabrics, and nitro compounds, they have many uses in explosives and pharmaceuticals. Finally, we can see that diazonium salts, they are used to prepare haloarenes. Haloarenes such as chlorobenzene, bromobenzene, iodobenzene and fluorobenzene. So these compounds, they are important building blocks in both laboratory as well as in industrial chemistry. So first let us begin with seeing the preparation of phenol. So the main focus over here is on converting a diazonium salt into phenol. So we will talk about the conversion of diazonium salt to a phenol. Okay. So I hope you all know by now what is a diazonium salt. So it is a compound that contains a special group which is called diazonium group. Okay, which is usually written as N2 plus and a halide like Cl. So this group is very reactive. It can be replaced by other groups. So one common method for this conversion is acidic hydrolysis. So in this process, we use an acid and water to break down the diazonium salt. Okay, so the work over here of acid is that acid help us to make the reaction go faster and ensures that the diazonium group is replaced efficiently. Now, to carry out this reaction, we warm the diazonium salt solution in the presence of water. So this heating, it provides the energy which is needed for the reaction to take place. One more important thing, that it is important to control the temperature because diazonium salts can be unstable as well as they can be decomposed if they are overheated. Now, during this reaction, the diazonium group, which is N2 plus Cl minus, it is replaced by a hydroxy group, which is the OH group. So, this means that the nitrogen gas is released and the final product is phenol. So, this is a good example of substitution reaction where one group is replaced by another group. So, look at this reaction. You will see we have a diazonium salt. When you treat it with H2O, we will see we get a phenol. Okay, you will see that this diazonium group, which is this N2Cl group, is replaced by the phenol. Okay, so see when this diazonium salts react with water and acid to produce phenol. Okay, and along with that, it also produces nitrogen gas and hydrochloric acid. Next, we will see the preparation of benzonitrides. So, what is benzonitrile? It is an organic compound where a benzene ring is attached to a nitrile group, okay, which is a carbon triple bonded to nitrogen. So, first we will focus on converting a diazonium salt into benzonitrile. Okay, so diazonium salt which contains N2 plus and Cl minus. So one important method for this conversion is Sandmeyer reaction. What happens in this reaction? The diazonium group is replaced by a different group using a copper salt. Okay, using a copper salt as a catalyst. So this is of how transition metals, they can help us change the structures of organic molecules. It is a classic example of this. So especially when we react a diazonium salt with copper 1 cyanide, which is this CuCN. So the cyanide group, which is Cn, it replaces the diazonium group and this forms benzonitrile. So the copper 1 cyanide, it acts as a source of both, okay, of the cyanide ion, and it also acts as a catalyst to make this reaction happen efficiently. Okay. So you will see over here the reaction which is showing this conversion of diazonium salt into benzonitrile using CuCN, which is copper 1 cyanide. So you will see this group is replaced by the cyanide group, which is the Cn group. Okay. Now we will see the preparation of nitro compounds. So for using the conversion of diazonium salts into nitro compounds, we see the mechanism which is involved in this reaction. Okay, it is nucleophilic aromatic substitution. What happens in this process? A nucleophile, which is an electron-rich species, it will replace a leaving group on the aromatic ring. So you will see over here the reagents that we use. So the diazonium salt, it reacts with sodium nitrite, which is NaNO2, and copper powder. So what does sodium nitrite do over here? It acts as the nucleophile, while the copper, it facilitates the reaction. So this combination allows the nitro group, which is the NO2 group, to be introduced onto the aromatic ring, displacing, or I can say replacing, the diazonium group. So look at this reaction. Here we have diazonium salt. When you treat it with NaNO2, which is sodium nitrite and copper, along with heat, we convert it into a nitrobenzene. So this group over here replaces by this group, which is the NO2 group. Now let us solve example 9.5. So it is asking, how will you convert 4-nitrotoluene to 2-bromobenzoic acid? So you have to convert this 4-nitrotoluene to 2-bromobenzoic acid. Let us see. So we are starting with the conversion of 4-nitrotoluene to 2-bromobenzoic acid. Now this conversion actually takes place in 5 steps. So one by one we will see each of the steps. Step number 1 is electrophilic substitution reaction. Okay, so electrophile, what happens in this reaction? Where an electrophile, it replaces a hydrogen atom in an aromatic ring. Okay, so you will see that in this step we add bromine to the molecule through electrophilic substitution. So over here bromine acts as the electrophile. That means it will see out the region, or it will seek out the areas of high electron density in the aromatic ring. Okay, so this is how we can selectively introduce halogens into aromatic compounds. Now over here, the bromine ion, which is written as Br+, it acts as an electrophile. Okay, so electrophile is a species that accept electron, and in this reaction Br+, it will be attracted to the electron rich aromatic ring. Now what will happen? Br+ can attach either to ortho and para positions relative to the methyl group. Okay, but the actual position depends on the directing effects of the groups that are already present. Over here you will see that only the ortho position is available for the substitution. This is because the para position, it is already occupied by the nitro group. See, it is 4-nitrotoluene. Okay, so at 4th position a nitro group is attached. So para position is already occupied by the nitro group. So where will the bromine go now? Obviously it is left with only one position. It will go at the ortho position. Okay, so if we'll see the reaction over here, you will see this is 4-nitrotoluene, 1, 2, 3, 4. On 4th position, a NO2 group is attached. Okay, and you will see it will undergo a electrophilic substitution reaction, and this bromine gets attached to ortho position. So this is ortho to this methyl group, which is CH2 group, because at para NO2 group is already attached. So it is only left with this ortho position. Okay, let's see now next steps. Now we will be moving to step 2. Now in step 2, we will see the reduction of the nitro group, which is the NO2 group. So what does reduction means? That means you are gaining electrons. Okay, so we will see that we will convert a group like NO2 group to a less oxidized form, okay, such as an amine group. So we will see over here that the NO2 group, it is reduced to NH2 group using tin and hydrochloric acid. Okay, that is SN, which is tin, and HCl, hydrochloric acid. So this is a very standard method which is used for reducing nitro groups in organic chemistry. Okay, so if we'll see over the reaction here, we will reduce now this compound, or will reduce this nitro group into NH2 group, okay, using tin and HCl. So this NO2 group gets reduced to this NH2 group. So step 2 is the reduction of nitro group. Now we will see the next step. Step number 3 is the diazotization reaction. Okay, so diazotization is a process where an amine group, especially an NH2 group, is converted into a diazonium salt. So we will see over here that the NH2 group, it is transformed into N2Cl group using sodium nitrite and hydrochloric acid at low temperature. So in this reaction, sodium nitrite, it reacts with HCl to form nitrous acid, which then further reacts with amine. And you will see this reaction is carried out at low temperature, because low temperature is essential to keep the diazonium salt stable, as it can decompose if it is warmed up. So look at this reaction over here. You will see over here, this is the diazotization reaction. So we have seen over here that this NH2 group over here, the NH2 group over here, it is being converted to N2Cl group. Okay, by using NaNO2 and HCl at low temperature, which is 273 to 278 Kelvin. Now we will see next. Now we are going to move towards step 4, which is a reduction of diazonium salts. So here we will see that to carry out this reaction, we need a chemical which is called H3PO2, okay, which is known as hypophosphorus acid. So this reagent is effective at reducing the diazonium salts. So you will see over here during this reaction, the diazo group, which is N2Cl, it is replaced by the hydrogen atom. This means we are removing the nitrogen group and adding hydrogen in its place. So if you look at this reaction, you will see reduction of diazonium salt. Over, we remove this N2Cl and we add hydrogen over here, okay, using H3PO2, which is hypophosphorus acid. Okay, so this is reduction to diazonium salt. Okay, so if you'll see over here, this is, we got this product. Now further moving on, we will see step 5, which is oxidation of CH3 group. So to achieve this oxidation, we use a strong oxidizing agent. Strong oxidizing agents such as potassium permanganate, which is KMnO4. Strong oxidizers like KMnO4, they are commonly used in labs to convert alkyl side chains on aromatic rings into carboxylic acids. Okay, so here we'll be using KMnO4. So as a result of the oxidation, the CH3 group, it is converted into COOH group, which is a carboxylic acid. Okay, so this is a transformation, and it is important to recognize over here that the entire methyl group is oxidized all the way to acid. So you will see over here that we are using a strong oxidizing agent like KMnO4, which oxidizes this CH3 group to COOH group. And here we get the product, which is 2-bromobenzoic acid. Okay, this is 1 and 2. So at second position, we have a bromine group, okay, which is ortho to this carboxylic group. So this is 2-bromobenzoic acid, which is our final product. Now we will see another in-text question, 9.9. In this question, you have to convert 3-methyl-aniline into 3-nitrotoluene. And second part is aniline into 1,3,5 tribromobenzene. Okay, let us see the solution now. So first is 3-methyl-aniline into 3-nitrotoluene. So this conversion will occur in 2 steps. Let us see one by one each steps. First is the diazotization reaction. What we'll do in this step, in this process, we convert the amine group on the aromatic ring into a diazonium salt. So we will see that here we react 3-methyl-aniline with sodium nitrite, which is NaNO2, and hydrochloric acid at low temperature. So this specific condition is necessary to form the diazonium salt and prevent any unwanted side reactions. Okay. So this low temperature, it helps stabilize the diazonium ion. So in this step, the amine group, which is the NH2 group, it is converted into a diazonium group, which is N2Cl. Okay. So here you will see that the diazonium group is much more reactive, and this can be replaced by other groups. So look at this reaction. Here you have 3-methyl aniline. 1, 2, 3. At third position, a methyl group is attached. When you treat it with NaNO2 and HCl at low temperature, so you will see this NH2 groups get converted into N2Cl, which is N2 plus and Cl minus. Now further we will see, next step which we are going to see is electrophilic aromatic substitution. Okay, so in this electrophile will replace a hydrogen atom on the aromatic ring. So you will see in this reaction that the 3-methyl diazonium salt, it reacts with sodium nitrite and copper salt. So this is a very, you can say this combination is used to introduce a new group onto the aromatic ring by replacing the diazonium group. So you will see at this stage the N2Cl group on the aromatic ring is being replaced by a NO2 group. Okay, so this is an example of a substitution reaction where one functional group is swapped with another. So see over the reaction over here, this is 3-methyl diazonium salt. Okay, when you treat it with sodium nitrite and copper salt, over here what you get, 3-nitrotoluene. Okay, 1, 2, 3. Okay, this is at third position, a NO2 group is being attached. Okay, so this is 3-nitrotoluene. Now let us see the another part, which is aniline into 1,3,5 tribromobenzene. So now this conversion occurs in 3 steps. First one is bromination of aniline. So bromination means we are adding bromine atoms to the benzene ring. Okay, so if you see over here, the amino group in aniline is a very activating group. So it directs the incoming bromines to ortho and para positions. So in this step, we react aniline with aqueous bromine, which is Br2 aqueous. So this reaction is very fast and it leads to substitution at 2, 4 and 6 positions on the ring. Okay, so the result is a tri-substituted product, which is 2, 4, 6 tribromoaniline. Okay, so it will yield a tri-substituted product. That means bromine will get attached to 2nd, 4th and 6th position. Why this happens? Because the amino group strongly activates those positions which make them more reactive to bromine. So look at this reaction over here. You have aniline. When you treat it with Br2 aqueous, you will see you will get a tri-substituted product. So 1, 2, 3, 4, 5, 6. At 2, 4 and 6, you get bromine atom attached. So this is a tri-substituted product. Okay. Now further we will see step 2, which is the diazotization reaction. So here we convert an amine group, which is the NH2 group attached to benzene, into a diazonium salt. So here we will see the reaction of 2, 4, 6 tribromoaniline with sodium nitrite, which is NaNO2, and hydrochloric acid at low temperature. Okay. So it is important to note that low temperature, usually around 0 to 5 degrees Celsius, is crucial for the stability of the diazonium salt. Okay, I'm again and again telling you that you need to carry the reaction at low temperature. So here you will see the NH2 group is converted into N2Cl group, which is the diazonium group. So the diazonium group now is they can be easily replaced by other atoms. Okay. So look over here, the reaction. You have 2,4,6 tribromoaniline. When it reacts with NaNO2HCl at low temperature, this NH2 group gets converted into this N2 plus Cl minus group. Okay. Now further, we will see step 3, which is reduction of diazonium salt. Okay, so this N2 plus Cl minus, which is attached to the benzene ring, this group will be reduced over here. So to carry out this reaction, we use hypophosphorus acid, which is H3PO2. So this reagent, it specifically reduces the diazonium salts. So you will see over here that the N2Cl group is replaced by the hydrogen atom. Okay, this means we are effectively removing this diazonium group and we are restoring a simple hydrogen in its place. So look at this reaction. Here we have this diazonium group, which is N2 plus Cl minus. Using hypophosphorus acid, we have reduced it and it is replaced by one hydrogen. Okay, so this is what we get. Now at last we will summarize whatever we have studied in today's lecture. Okay. So first we talked about the diazonium salts. They are valuable synthetic intermediates. That means these are the compounds that help us create many other useful chemicals. So they are very valuable synthetic intermediates. Okay, so they can easily be converted into various functional groups. So this flexibility is what makes them so important in synthesis. For example, by changing the conditions, we can turn a diazonium salt into a phenol or halide or even a nitrile. So we have seen that they can be easily converted into various functional groups. Okay. So now look over here the various reactions of the diazonium salts. Okay, so if we specifically start with Cu2Br2, Cu2Cl2 and CuCN. Okay, so this is basically the Sandmeyer's reaction. Okay, this is cuprous. If you'll see, this is cuprous chloride, this is cuprous bromide, and this is cuprous cyanide. Okay, so these are dissolved in the corresponding halogen acids like hydrochloric acids for chloride or hydrobromic acid for bromide. So the choice of the salt and acid determines that which group will replace the nitrogen in the aromatic ring. So if we are using cuprous bromide, okay, first if we are using cuprous chloride in hydrochloric acid, then the nitrogen group over here will be replaced by this chloride. Okay, and N2 gas will also be released. Similarly, if we are using cuprous bromide in hydrobromic acid, then the nitrogen group is replaced by a bromine atom, which is forming an aryl bromide and a nitrogen gas. Okay. Finally, if we use cuprous cyanide, okay, this you'll see over here, if we use cuprous cyanide over here, or either we can use potassium cyanide. So the nitrogen group will be replaced by a cyano group, which is C triple bond N, which gives us aryl cyanide and a nitrogen gas. Okay, so this is a very useful way to introduce a nitrile group into an aromatic ring. Now if we see the Gettermann's reaction, okay, in this Gettermann's reaction, we use cuprous halide. In Gettermann's reaction, if we're talking about Gettermann's reaction, then instead of using a cuprous halide, we use a copper metal along with the appropriate halogen like hydrochloric acid. So this is a Gettermann's reaction. Okay, we are using copper metal powder along with a halogen acid. Here specifically we are using hydrochloric acid. So this method is specially useful for preparing aryl chlorides and even bromides from aromatic diazonium salts. Okay, so this N2 group is replaced by this Cl. If we are using over here, if you see we use hydrobromic acid instead of hydrochloric acid, then over here we will get aryl bromide. Okay, so over here if you see we are getting a aryl bromide. Now we will see the method for preparing aryl fluorides. Okay, if you'll see over here, that is, if you are preparing aryl fluorides from aromatic amines, then the reaction is Bals-Kieman reaction. Okay, so in this reaction we start with the aromatic diazonium chloride and we treat it with tetrafluoroboric acid, which is this HbF4. Okay, so this causes the formation of a solid which is called aromatic diazonium tetrafluoroborate, which separates out as a precipitate. Okay, then in step 2 we take the precipitated aromatic diazonium tetrafluoroborate, filter it and dry it, and then we heat it. So this heating, it causes the compound to break down, releasing nitrogen gas and forming this desired aryl fluoride. Okay, so this is Bals-Kieman reaction. So this is the step where the actual displacement of the nitrogen happens, which results in the introduction of fluorine in the aromatic ring. So here we see that next if we see when we use a mild reducing agents, okay, like we use hypophosphorus acid, which is H3PO2, or we use ethanol, which is CH3CH2OH. In that case, they can be used to reduce the diazonium group into aromatic diazonium salts. Okay, so if you'll see the diazonium group where a nitrogen is attached to a aromatic ring. So these agents, they help remove the nitrogen group and themselves they get oxidized to phosphorus and ethanol. Okay, so the aromatic diazonium, which is ArN2 plus Cl minus, it reacts with hypophosphorus acid and water to produce benzene. Okay, as well as it releases nitrogen gas, phosphorus acid and hydrochloric acid. Okay, now next you will see when the diazonium salt, it reacts with warm water or steam to produce phenol. Okay, if you look at this reaction, earlier we talked about this reaction. Now if you are moving on to this reaction, so here it reacts with warm water or steam to produce the phenol. So the key point is that nitrogen group is replaced by the hydroxyl group. So you will see it replaces by this OH group which forms a phenol. So this reaction also releases the nitrogen gas, which is a physical change we can observe as bubbles. Okay, so this is about the various, you can see the diazonium salts. This can be easily converted to various functional groups. Okay, so we saw Sandmeyer's reaction, we saw Bals-Kieman reaction, we saw Getterman's reaction. Okay, so this is, you will see the versatility of the diazonium group. Okay, so thank you students so much for your attention. I hope this lesson was useful to you all. Thank you.